Good morning, ladies and gentlemen, and welcome to the 14th Concawe Symposium. I am delighted to welcome you here this morning, here in Brussels, in our studio, for this two-day live event, and I will be moderating this event. My name is Alain Mathurin, and I'm Communications Director in the association. The 14th Concawe Symposium was previously, in the other editions, a live event with people in the room. This is, of course, the new rules that have obliged us to have this. We usually were gathering about 175 to 200 delegates for the 2 days event. And I have to say that I would like to thank all of you for being here. We have almost 800 people that registered for this 2-day event. This is just amazing, and even food for thought for the next editions. I'm convinced from the program that we have put together that we will have the opportunity to witness compelling and inspiring sessions. And I'm looking forward to live these sessions with you today and tomorrow. A few practical aspects before we dive into the real discussions. You will have the opportunity to interact with our speakers after each of their individual interventions. You will see on the right side of your screen a little chat box. You can put your question in the chat box, decide whether you want to put it in person or anonymously, and just send link. And I will receive it here on my iPad, and then we'll replicate that question to our speakers. Some of the speakers will be with us in the room. Others will be connecting from abroad, and we'll manage this with our great team here in Brussels. You can also follow Concawe on LinkedIn. Social media today and online websites are key tools to inform. So we have a Concawe LinkedIn page. Don't forget to follow us. There will be a lot that will be posted about the symposium, and if you don't follow us, that's a great opportunity. I'll maybe take this opportunity to introduce our first speakers for this first session. We have 4 distinguished speakers who will talk us through many different technology options. First speaker will be Professor David Chiaramonti from Polytechnic University of Turin. Good morning, David. Our second speaker will be Jiří Hájek from the company Orlen Unicre. Good morning, Jiří. Third speaker is Giacomo Rispoli from NextChem. Good morning, Giacomo. And our fourth and final speaker that will make an individual presentation is Tijs Lammens from BTG Bioliquids. Good morning, Tijs. We will then be joined by a Concawe science executive after this presentation by the 4 speakers, but I will introduce Marta in due time. Perhaps, David, we are, I think, ready to move to the first presentation. So let's start with you. Very brief introduction, very brief bio. You have it, again, I repeat it in the program that you have received with your confirmation email. Some bios are quite long, but just read them out. David Chiaramonti, PhD, full professor of energy systems and energy economics at the Polytechnic of Turin, and chairs the Renewable Energy Consortium for R&D, RECORD. Awarded the Lindenborg Prize for Outstanding Merits in Biomass at EUBCE, European Biomass Conference and Exhibition in Stockholm in 2017, and included in the Stanford University list of 2% most cited scientists. And just to say this, a few elements. Authored more than 180 publications, participated into more than 27 EU R&D projects. Former member of the IEA Bioenergy Task, today member of the UN ICAO Task Force Fuel Transport Group on Alternative Fuels for Aviation, and this is just a little part of your long journey. David, the floor is yours.
Thank you. Thank you very much for the kind introduction. I'm very, in the meantime, as switch to my presentation. It's a real pleasure being here with you. Also in my new role of Vice Rector for International Affairs, which applies very well to this kind of events. Well, I don't want to waste time. In my presentation, I will focus on some key elements, also taking in consideration that following speakers will perfectly address issues in refining, in gasification, in conversion of syngas and fast pyrolysis. So I did my best not to duplicate information that I'm sure will be presented in the following one. We are all aware that we are in the middle of an unprecedented challenge. We know very well how complicated and challenging is to meet the 2030, 2050 targets with such a huge decarbonization pathway ahead of us. From an industrial and policy point of view, however, I wish to remark one point. The waves of innovation are happening faster and faster with time, and the peak is more pronounced, more strong. So industry and policy making are challenging this situation. They have to develop actions that are compatible with this physical reality of innovating. So the questions becomes what is doable in a reasonable time frame that follows these waves. If this can meet the urgency need we had due to the climate challenge, and also as remarked a couple of weeks ago also by Timmermans, which are the socio-economic impacts of the introduction of innovation and how to build consensus. I like to repeat that one of the Green Deal most important point is no one left behind. That is also a very important value for our community. So I was invited to talk about thermochemical conversion, which mostly is fast in general, pyrolysis, gasification, hydrothermal processing, hydrotreatment. So in a biorefinery context, this is the part where you operate at a high temperature with catalysts and all steps we all know. However, it's a major point for me to remark that this thermochemical pathway more and more should be seen as an integrated way with biochemical conversion. Just to make very simple example, in a lignocellulosic ethanol plant, we do have a biochemical processes based on enzymes and yeast producing alcohol or a variety or other fermentation products. And then we have the lignin part that could be very well treated with many of these thermochemical processing systems. And probably the real best economic solution is the one that integrates this variety of options into a single wall. Among these, I will focus a bit on HCl and slow pyrolysis, because fast pyrolysis, gasification, and refining, I know will be subject of the following presentation. This is from the latest work that was mentioned before by Imperial College, but in reality, Dr. Maniatis developed this already in 2017, as many of our graphs are being adapted regularly. It identified the level of maturity from commercial to FOC deployment or development of the different pathways. And we see that indeed anaerobic digestion and lipid-based technologies are commercial, assuming that there are economic conditions, of course, but they are from an industrial scale perspective. Then we have lignocellulosic biomass that can be converted also through fermentation into a range of products. Can go from ethanol to even to jet fuel. And then we do have synthetic biofuels, paraffinic biofuels, again focusing on jet, marine, that are in the development phase and with several interaction each other. I mean, most of this process, as said, produce several products, liquid, solid, and gases that can be conveniently integrated and regenerated. Let me make one small remark. In the future, we expect very, very cheap electricity. The latest IRENA report was showing a cost of 5.3 to 2.8 cents of dollars per kilowatt hour, which means roughly a minimum of €2 per kilowatt hour, euro cent. So it means that variable renewable electricity is becoming cheaper and cheaper, and this can become an option also for thermochemical processing. Reactor could use this sustainable, cheap electricity also in their operation, and the design would change in that case. Another common message I always give in this kind of events is that industry take time to bring to market. Yes, that's the example of the Pyro that BTG will speak later. And another example is Enerchem from Canada, waste to methanol. Well, the story of these projects started in the lab around the second half of the 80s. And then today, actually 2015, around that years, we came out with the first real full-scale demo industrial plant. And that's, you know, the time industry needs to bring innovation to scale, actually. Of course, today we have some advantage because many of these technologies already went through this pathway. So we can act a bit quickly, but if you plan this if you put this in the so-called mountain of death, well, actually what you see is that HVO is fully commercial. Others are coming very, very rapidly, even I would say, like fermentation of CO2 to ethanol, the conversion of HVO to HEFA for jet application. Fast pyrolysis in co-processing particularly is ramping up quickly, and policy is following. And also gasification to various products from Fischer-Tropsch, but also to methanol and ethanol is quite close. It's in the first of a kind, and a lot of attention is given to waste-based feedstock in that area. Also, HTL and e-fuels are coming. There are some scale-up projects in the hydrothermal liquefaction phase. E-fuels are a major point in European policy, and we can expect a contribution between 3 to 5% probably by 2030 with e-fuels if the policy follows. These slides has already been shown, so I will only pick up from here a key message that, as you can see, Concawe estimation, which I personally agree also, expect the ramping up and the scaling up of these technologies, particularly lignocellulosic and e-fuels, post 2030, 2035, in the sense that one thing is having a demo plant, another thing is having many industrial scale plants producing million tons of products. So that's a kind of misalignment with the European policy that should be considered. Biomethane also can help a lot in the transition, contributing significantly in certain countries. Following this, the net zero IEA report came in, which is very aggressive and on the other hand, compatible with the targets we have set, with the goals we have established. Roadmap, that's a very strong roadmap with, no more internal combustion engine car sales at 2035. Clearly, compared to previous IEA study like this one, in the sustainable development scenario, 2 degrees, the sustainable development scenario by IEA, the contribution of the different sectors was, a bit different, even at 2060. Now there's an acceleration clear. The question is, are we able to follow this such strong path? I will focus now in my last part of the presentation on a couple of issues. One is thermochemical conversion from pyrolysis gasification. That's a process that always produces solid, liquid, and gas, and it requires dry feedstock, and it can operate at very different conditions. It quite good level of maturity in general. More or less feedstock sensitive depending on the type of process that we consider. Hydrothermal processing instead is mostly hydrothermal carbonization, hydrothermal liquefaction. For fuels is liquefaction, which operates in very severe conditions. 220 bars, 374 degrees is the critical point for water. It operates in a slurry conditions where up to 23% of solids is contained into the liquid phase, which is normally water, but not necessarily just that. technically speaking, is obviously a challenging type of plant, which is scaling up in Canada, in Norway. Few pilot installation exist in Europe, particularly in Denmark, Italy, a few other places, and US at PNNL mostly. It processes very wet feed. On the HTL side, there are routes for development in that period. The focus, again, as in all this sector, is being assigned to residual waste feedstock, and there are companies like Genifuel, Steeper, ENI, Mura already working at demo scale on this feedstock. There's the possibility to co-liquefy feedstock with some advantages for the technology. Not to forget the relevance of water management. I will come back to this in a moment. Co-refining could also work similarly to what is being done for fast pyrolysis bio oil, even if we have to consider that getting less oxygenated biocrude is an advantage, but it is very viscous stuff which can contain heteroatoms, and also supercritical CO2 fractionation is under deep investigation. I wish to focus a second on phase management, water phase management, because in water we do have soluble water organics. These can be treated in various ways, even catalytic hydrothermally gasified, or even digested through biochemical process, again in the case of integration between bio-based and thermochemical-based processing. But one thing I'm very keen is that this can be used for hydrogen production. And in the group, in the joint group, Polytechnic of Turin and Record, we have applied a technology named aqueous phase reforming, and the amount of hydrogen is quite relevant compared to the amount of dry hydrogen needed theoretically to refine the biocrude that is obtained, from 40 to some 70 to 80, depending on the feedstock type and process condition and other elements. So the water phase, which inevitably needs to be recycled in processes like this, is a good source, can be a good source of a green hydrogen in a fully circular form. In my last part of presentation, I wish to show also some innovative scheme beyond the technology, combining bio and thermal. That's an example. Many decentralized natural gas plants that use the natural gas grid exactly the same way as we use the electrical grid with photovoltaics and wind energy. And this natural gas deliver an equivalent amount of volume of natural gas to a centralized processing facility that can then deliver Fischer-Tropsch methanol, ethanol, and many other products. The guarantee of origin is the mean to guarantee that there is no double carbon counting for this carbon, and that exactly the amount of normal cubic meter delivered by natural gas is delivered to the centralized processing. This is based on mass balance. Italy can rely on more than 33 almost 1,000 kilometers of gas pipeline. So it's a good way to deploy the existing infrastructure and to deliver from the gas a product that is needed. Also delivering benefit in a decentralized way, so creating consensus. Another possible approach is so-called biomethane or methane pyrolysis or cracking, or direct methane decarbonization. This is a site in the US which already reached 5,000 tons per year hydrogen production through thermochemical processing of the methane. This is done in a special way in a process developed by École des Mines in France for more than 25 years ago. But there are other ways to do this. We have developed a very original other route to process the methane into carbon, solid carbon, and hydrogen. The interesting thing is that it promises to be very competing. I remind you that today we are in the range of $4 per kilogram of hydrogen. while our target is $1.5 per kilo of hydrogen. This biomethane pyrolysis seems a promising way to do to reach this target, even if TRL is lower, and there are a number of competing solutions like ours, like the one I've shown, that needs to be further developed. That's the moment to invest in this. Aviation has been mentioned as a priority. ICAO, which I participate, this team, has shown a huge need to intervene through the CORSIA program. It can be very well targeted by gasification and pyrolysis. Personally, I have my opinion that pyrolysis can very good target maritime for a number of reasons related to the biocrude characteristics. One thing we will be working from next January on is to try to develop the so-called European clearinghouse, which is a body similar to the one already existing for a long time in the US. It's called US Clearinghouse, based in the University of Dayton, that assists the ASTM certification of new pathways for the economic operators. There are roadmaps planned, like this one from the Netherlands. My feeling is that commercial scale is a bit optimistic, also compared to the previous slides I've shown from Concawe Fuels Europe and also our own estimation. But in this range, you have catalytic hydrothermolysis, Fischer-Tropsch, synthesized isoparaffins, pyrolysis, HTL, power to X. There are many routes that are thermochemically based, and that will represent a majority probably in the period post-2030. Let me conclude with by broadening the vision, my last minute. We have a serious issue in respect to the soil. The soil is getting in a very hard situation with no carbon, with low microbial activity, and this is impacting on agriculture as a whole, not on energy only. This has already been remarked by European institutions that are calling the Commission to take action on that, and there is a mission on soil taking air. We're talking about 50% reduction corn, wheat, and sugar beet maize in the worst case scenarios. So it's a dramatic situation. Well, in that respect, we are managing an ongoing project with Total. Probably we will have a new oil company entering this project very soon, where in Spain we have recovered the land with biochar, which is a co-product or a product of the thermochemical processing. And the nice thing is that we are cultivating camelina to produce jet fuel through the HEFA process, but in rotation on the same land without intervention, we are producing barley, which is food and feed. And the results are extremely promising. A land that would not provide any type of agricultural product is now back to reasonable production. Not only it is storing carbon through the biochar in the soil, which is compliant with the ETS, CORSIA, and offsetting measures. At the same time, it is a clear example of low ILUC feedstock. So it goes. It is not capped in the conventional part. It can deliver lipids to the HVO and EFA. We will be working further on this scheme that supports also agriculture. So my conclusion and my last remark are that clearly thermochemical conversion of biomass and waste and also gases, I would add, is expected really to be a leading actor in the ecological transition, given also the possibility to process many different feedstock, either bio-based, but also circular carbon-based. Nevertheless, scale up and full industrial scale replication to generate a million tons of equivalent product will likely happen after 2030. So we have to draft a credible roadmap. My recommendation to industry is to focus on the whole value chain and not just on the fuel production step. This comes from the typical oil thinking in refining, but in that case, the impact of the value chain is wider on the society. This will complement other biofuel chain. There's no competition at the moment, but there is rather complementarity. It is clearly a policy-driven market, as we all know, framed in Green Deal, Fit for 55, ICAO, IMO regulation, and the common request by all industry over the last 10 years, I always hear this, is to go for a stable and doable policy needed so that investments are secured given the large capex they are engaged. Last word is about economic recovery. As already said immediately, March 2020, by Nobel Prize Stiglitz, the post-pandemic world countries will focus on domestic chain as a mean to recover the economy. And I think that that's a great opportunity for bio-based recycled carbon, low carbon. We're just publishing a paper on low carbon aviation fuels in these days. All these are injecting economic resources into the economic system that will promote the recovery. So that's a strong argument for our sector. So thank you very much for the attention. And of course, I will be glad to participate to the discussion and answer any question later on. Thank you.
Thank you very much, David. Thank you for this very interesting first presentation of our symposium. I already see that we have some questions in the feed, but just one question I would like to open with. We will have a few minutes now and we have other questions in our panel session. Let's remember that. This is about the transformation of the refining industry, the way it has to rethink the way it works. You mentioned the value chain, that we have to move away from a fuel-focused value chain into a broader value chain. Could you tell us more about that?
Yeah, I mean, our installation are always large plant with large capex, large flow of biomass or materials. So clearly, in order to develop industrial scale installations, we need to be consensus, to create consensus. And indeed, my point is exactly that this is possible. The example that I have shown was just to try to materialize this concept with the energy resources that are concentrated on producing jet fuel. I am supporting agriculture in a very difficult areas, the majority of the areas in Spain. So that's an example where you clearly, with the value chain approach, support other sectors that are facing very difficult times through the production of truly sustainable fuels and improving the biodiversity, having many, in a cascade approach, many other benefits. This creates the consensus. This makes a more positive attitude to building new plants or adapting new plants and reinjecting resources into the society. That's why I'm saying that the value chain approach is needed. The refinery is part of a community in this transition, this ecological transition. And as said by Timmermans, and I close with that, we must absolutely avoid a conflict between ecological transition and social issues, but they should rather go together to go to the PIMBY concept, please in my backyard, and not NIMBY, not in my backyard.
Thank you, David. I have a second question because I saw your last slide, which was of interest when you touched on the soil challenge. Do you see any risk here that this could undermine significantly the biofuel value chain because of this situation with the soil for the moment?
Well, on the contrary, I see to be optimistic in a difficult time for the soil, but I see a great opportunity, as I said. The problem is rather to explain properly what we're doing to the general public. Bioenergy tends to be more complex than wind or PV, indeed. But these actions are needed. What is the alternative? The alternative is that the soil is marginalized and abandoned. Just in Europe, I'm citing studies by Calliope that will close this, Imperial College that will close this symposium. We do have 8.5 million hectares only Mediterranean area of marginal land. So you can forget about energy. Try to figure out the impact on the society of such a huge amount of land which is marginalized. What we can do is to support farmers to produce the feedstock for energy as well as other feedstock that otherwise would not be produced. To link to a term that is very common in the fuel sector, that's a case of reverse ILUC. I keep in production a land that would otherwise be shifted elsewhere with a typical ILUC concept. So these kind of things are hard to explain, I understand, but it's what we can do. And this, to conclude, gives us the possibility to cherry pick also other from other basket, like the carbon, ETS scheme, CORSIA scheme, offset scheme, hard to abate industries, they have to decarbonize. So we can create a symbiosis with this kind of industry, delivering to them what they need and delivering bio and supporting agriculture. But we need this holistic view, which of course is more complicated than a very simple linear approach. But I trust is the only way we can succeed.
Thank you, David. Just 10 seconds. Would this also enable to improve biodiversity?
Well, of course. Marginal, arid, desertified, salinized land indeed is loss of biodiversity, loss of microbiota. If we inject biochar, compost, if we cultivate perennial or annual, biodiversity is indeed improved. I'm not a biologist, but that's an obvious conclusion. There's more biodiversity there than in the desert in other ways.
Thank you very much. We'll continue our conversation in the panel after the other speakers. Let's now turn to our next speaker. This is Jiří Hájek, joining from, if I'm right, the Czech Republic. Good morning, Jiří. Very brief introduction before I hand you the floor for your presentation. You are CEO and Chairman of Board of Directors, Unipetrol Center for Research and Education. You started in Unicre in 2014 and brought with you the experience that you gained as a senior process engineer in the Česká rafinerská, focusing mainly on HCUs and HDS. As a CEO of Eurosupport Manufacturing Czechia, you currently focus on biofuels integration in Unipetrol refineries, utilization of waste plastic in petrochemical segments, and hydrogen mobility deployment in the Czech Republic. I hope I was short enough. Floor is yours.
Thank you very much, Alan. And thank you very much, Concawe, for this great opportunity to present today the outcomes of our, research that we have conducted over the last couple of years, particularly focusing on advanced biofuels production. The first slide that I would like to share with you is basically originally from Fuels Europe, and actually it has been already presented in, new version by Luis a couple of minutes ago. The truth is that the refineries will have to adapt to the situation that in the future there will be a clear need to process a part of traditional crude oils, also biogenic waste materials, or later on we will switch to the CO2 conversion to either gaseous or liquefied products, as well as waste conversion. So from our perspective, all the products that we will produce in the future will certainly contain certain proportion of biogenic material. I would like to very briefly discuss why do we have to do it. And shortly, I may say that actually the ambition is, of course, to achieve the compliance with the Renewable Energy Directive, either the second edition or the third edition, which is currently under discussion. And essentially, we are forced to reduce the carbon footprint of the related, which is related to the automotive, marine, and of course, aviation fuels utilization. What is the key focus? in previous presentation, we have learned that actually there are multiple sources of biogenic material that we can adapt. Particularly in our achievement, we are mainly focusing on materials such as forest residue and agricultural residue, as well as municipal waste conversion. The key challenges associated with the processing of this sort of material are, let's say, focusing on biogenic based material provision. Particularly at this moment, the effective collection has been not clearly organized in most of the countries across EU. We know that the storage and pretreatment is also subject for further discussion, and ultimately, not everybody is capable to prepare a sufficient set of analyses which are required. The technology maturity of individual technologies is still subject for further development, because currently there are only a few companies which can really deliver pilot scale in fully functional pilot scale technology, while fully adopted commercial scale technologies are still in the process of development. Feedstock flexibility, wheat quality sensitivity, and the yield of desired products are basically determining the success of such a project. Nevertheless, still the commercial scale range has not been proven yet, and that's why we also need to think of whether it is wise to put our risk into the installation of the new technologies, or rather to focus on utilizing the existing technologies and partially co-process a certain proportion of the biogenic waste material. And finally, we also need to think of how those products will influence the parameters, the key crucial parameters of our traditional products, such as gasoline, particularly research octane number, cetane index of diesel, eventually stability, and the oxygen content. Well, I would like to briefly share with you the outcome of our COMSIM concept, which we have studied over the last couple of years together with the colleagues mainly from VTT from Finland and other partners from Germany and Italy. Well, the concept was focusing on the gasification of forestry residue, and it was basically aiming to convert the gasified material into Fischer-Tropsch products and accommodate those Fischer-Tropsch products either in the refinery or eventually introduce them to the steam cracker. Well, the ambition was to deploy the concept which will enable us to operate a unit with a capacity of 150 megawatts at the gasification stage and reduce the emission in contrast to the alternative routes by 35%. And actually, we wanted to deliver the fuel with the cost below €1. Actually, the range, the aspiration was to achieve 80 cents per liter. Ultimately, the overall aspiration was also to achieve greenhouse gas savings in the range of 80%. And similarly to the efficiency should have been elevated. What we have achieved shall be demonstrated on an upcoming slide. For those who are not very familiar with the entire process, with the entire concept, I would like to stress that the gasification and the consequent Fischer-Tropsch technology produce not only gaseous, but mainly liquid products. Not only liquid products, but also waxy products. The yield or the split can be adjusted according to the needs of the particular operator. But we can say that in our case, we were targeting mainly the hydrocarbons boiling in the range of 140 to 240 degrees C, but also we produce significant amount of waxes, which shall be effectively introduced as a feedstock to the existing hydrocrackers. So in principle, I would like to stress that the flexibility of the operation of the particular Fischer-Tropsch technology very much depends on the desired operating on the desired yield pattern, as well as on the operating conditions of your technology. What can we achieve by doing this? We may say that actually we can produce diesel range material which is meeting the specifications, particularly cetane index shall be really higher in contrast to, for instance, traditional fossil fuels, as well as sulfur content is by far below the threshold. Nevertheless, we need to stress that the CFP the cold flow properties are actually somehow limiting the utilization of this material, at least in the central and northern part of Europe, only to the spring and summer. That's why the hydroisomerization step is for sure needed for operation of such a technology. Well, we did our exercise and we did our simulation considering utilization of the waxes as a valuable feedstock for our hydrocracker. And we can say that actually by doing that, we have achieved the reduction of greenhouse gases emission really below 80%. Nevertheless, all the costs associated to the transport of the let's say biogenic waste material to the point of gasification and also the transfer of intermediate products are still significantly influencing the operating cost, and that's why the cost of production of biofuel achieved was in the range of 1.1 euros per liter. We can also say that actually there was a break-even price to introduce such a material on the market, and it was calculated in the range of 1.7 euros per kg. What I would like to stress here is that actually in our calculation we also we mainly calculated the benefit of introduction of the green fuel to the market. Nevertheless, we still abandoned or actually we didn't take into consideration the benefits associated with the introduction of the green feedstock to the existing steam cracker, just because simply there is currently no demand for the biogenic plastic materials. But hopefully this will come up very soon. What are the particular outcomes and conclusions which we have experienced? Well, I would like to stress that actually introduction of the biogenic waste or let's say the Fischer-Tropsch waxes to the steam cracker enabled us to increase the yield of the desired product, particularly naphtha or gasoline and light ends. In contrary to that, the yield of kerosene was actually pretty much in the same range, independently on the amount of Fischer-Tropsch products in the feedstock, while contrary, the yield of gasoline was reduced significantly. The same thing we can conclude about the yield of, let's say, waxes or residual material, unconverted oil from the hydrocracker. The yield of the unconverted oil was also reduced. And we may see some unexpected even that the sulfur content was rising up. But don't get me wrong, this is mainly a function of the temperature, and it has nothing to do with the content of the Fischer-Tropsch product in our feedstock. What appears to be very promising, and what I would like to encourage other audience who are operating steam crackers to think of, is the introduction of the Fischer-Tropsch waxes, particularly to your existing steam crackers. It appears that actually in all aspects, the introduction of the Fischer-Tropsch waxes to the steam cracker has a significant or positive impact on the yield of desired products, such as ethylene, C3 or C4. On the other hand, the yield of benzene and let's say heavier hydrocarbons was reduced. So it very much depends on what is the what is typical for your particular refinery or petrochemistry, whether you want to produce lighter olefins, then introduction of the Fischer-Tropsch waxes might be considered as a very interesting option, while contrary to that, if you are focusing on benzene and petrochemical oils, pyrolysis oils, this probably would not fit to your business case. So what we have achieved and what are the particular achievements of our studies? Considering the existing renewable energy directive, I would like to stress that actually, if we can still double count the emission savings associated with the waste renewable material introduction, we can achieve the required 80% savings. Nevertheless, it is a still question whether this will, let's say, premises will last also in the upcoming years when the new introduction of renewable energy directive is expected. In our COMSIM project, we realized that actually the value of introducing the Fischer-Tropsch product is really high, especially with the increasing requirements associated with the appearance of advanced biofuels on the market. It's very likely that this sort of technologies will have to be introduced in most of the refineries that would like to survive the year 2030. Nevertheless, the question is whether there will be a chance to either exploit the existing asset, which will very likely suffer from the lack of demand for traditional fossil fuels, or whether we will go in the direction of installation of the new technologies. In addition, I would like to stress that actually all the Fischer-Tropsch products did not jeopardize or harm the properties of the traditional fossil fuels. In generally, we may say that actually they even improve most of the properties, and those who needs to be improved either octane number for naphthas or cetane index for let's say diesel range material have to be, of course, adjusted to the particular location. What we would like to highlight is that actually operation or processing of this sort of material at your steam cracker, or if you have a surplus of Fischer-Tropsch product, you can increase the value of your petchem by introducing this sort of material, because the range or the yield of the desired product shall be significantly increased by particularly processing of linear hydrocarbons. And ultimately, the processing and co-processing of waste material can somehow secure the operability of the existing refineries, which are struggling and adjusting their strategies to the, let's say, recent calls and recent requirements for greener and less carbon demanding, less fossil carbon demanding fuels. So in principle, there are a lot of benefits associated with the operability of the refinery processing, let's say, biogenic waste material. Nevertheless, we still need to take into consideration also the risk, and the risks are associated, or the challenges are associated with the feedstock availability, as well as with the maturity of the existing technologies. At the end of my presentation, I would like to thank, first of all, the European Union to provide us funding for the operation, or for the realization of our research, which was led by WDT in Finland and in collaborative consortium among Ineratec, Orlen Unicre, and the colleagues from Wood, EFRI, and Center from Germany. So thank you very much for thank you all the audience for this possibility to present you our presentation, the outcomes of our R&D activities, and I'm very looking forward to see and to hear your questions.
Thank you very much, Jiří. And indeed, there are a few questions from the audience. I also have a few questions for you. I'm reminding everybody, don't forget to put your questions on the right side of your screen. You have a chat box, just post them. I have seen a few coming in, and one of them fits with my introductory question, which was about, you mentioned some prices. So I had, in fact, initial question was to see whether to reduce the cost, because you've mentioned a cost of €1.10. We're not going to enter into the detail of it, but if you were to put the entire hydrocracking system also closer to the production place, could you not take the price down? And then I have a question from Michael Pope, who wanted to know whether this €1.10 also includes capital expenditure, so or capital costs. So that would be our introductory question.
Okay, so thank you very much for this question. I will start with the second part. It does not include the capital expenditure. So actually, all the costs are mainly related to the introduction and the operation of the asset, either the new one or the existing one. And actually, we calculate the cost of feedstock, the operating cost. We didn't take into consideration the depreciation, or basically, the cost of installation. Nevertheless, considering what you have asked for, of course, it is valuable to very likely introduce the technology as close as possible to the source of the original feedstock. Our ambition was to, however, limit the or reduce the capex, basically capital expenditures associated with this project, because already the cost of the product appears to be significantly higher in contrast to the traditional fossil material. And that's why if you want to deliver this material to the market and we want the customers to pay for it, we simply need to deliver the product at the competitive price. So either with the subsidies, we would very much struggle to be really comparable with the traditional fossil materials, and that's why our ambition was simply to reduce it. The second aspect, which we need to take into consideration, is the emissions associated with the transportation of the either biogenic waste material to the port of processing. In our understanding, it would be the best scenario, which we have evaluated, shows that preferably the gasification and the Fischer-Tropsch technologies should be as close as possible to the source of the feedstock. But there is a premises which needs to be into the consideration. There must be a hydrogen, independent hydrogen supply needed. So if you want to operate such a technology such as Fischer-Tropsch, you need to have a significant surplus of hydrogen, and then easily you can transport or ship your waxy or liquid Fischer-Tropsch products to the further processing sites.
Thank you, Jiří. You mentioned the challenge of biomass availability in your conclusion. And do you see risk of competition with other sectors, thinking of power generation as an example?
Exactly, and actually, in this case, I would say that we are slightly in disadvantage because probably the colleagues from Imperial College will touch upon that later during this symposium. What we see today is that well, there is already a market for waste biogenic material, and it's being traded, but only a very small proportion of this material is ending up in existing refineries or any biorefineries, and it's being utilized for production of the biofuel components. Indeed, most of the product, the biogenic waste material, which is being today effectively traded, is ending up in the energy sector, which is, at least in our country, representing 4 times more CO2 emissions, and that's why logically we can conclude that they will need even 4 times more biogenic waste material to achieve compliance, which is addressed to the energy sector. So for sure, there will be a competition, and we do not know yet whether there will be enough for refinery and energy at the same time. Probably not.
Let's see, we have another session around that tomorrow. But again, we take this as a serious challenge specifically from a national perspective when it comes to the Czech Republic. Just one very short 10-second answer. What is the scale of the experiment run in the COMSYN project?
Okay, the pilot scale technology was installed in Finland, and actually it was able to process the 5 megawatt gasifier, while in our case we were targeting to produce a few hundred kilos of, let's say, diesel range and diesel range material as well as waxes.
Okay, thank you. And I'm now delighted to welcome for his presentation Giacomo Rispoli. Giacomo will join us from Italy remotely. He holds a degree in chemical engineering from the University of Rome, joined Eni Refining and Marketing in 1986, spending 5 years working as a process engineer for an engineering company before that. He is Executive Vice President of Portfolio Management and Supply and Licensing Department, signed off more than 20 patents in the field of biotechnologies and on the bottom of the barrel upgrading. I hope with this I do summarize your career, Giacomo, and we're glad to hear about waste to chemicals, a new concept of biorefinery. The floor is yours.
Okay, yes, thank you very much. You summarized very well. Now I'm working with NextChem in the Thermochemical group, and it's a pleasure to me today to talk about this new concept of a biorefinery. So to go ahead, okay. I'm going in my presentation to describe this new concept that in the next CAM we generated of this biorefinery. We are going to use waste, municipal solid waste as a resource, and then few words about the product's valorization and my conclusion. Next. Sorry, to go. A few words about the group where I work. The company is a Chiaramonti Group, is an Italian engineering company with more or less 10,000 people working in Italy abroad. Most of the activities are generated and most of our revenues is generated abroad. This company 3 years ago founded the NextChem, where I'm placed, and in NextChem we are working on the new technologies for the future. Okay, first of all, why a new concept of a biorefinery? I worked in the past a lot, and you said also that I wrote many patents on biotechnologies, and in particular to generate biofuels. But why this? Because in 2009, everybody knows that we had a red in Europe because with the red and the fuel quality directive, any oil companies was forced to make use of biocomponents in the fuels in order to reduce the CO2 emissions from internal combustion engines. And so going ahead, and so the products that we have to generate from as a biocomponents, at the beginning we have and we still have fame for diesel, we have ethanol for gasoline, we have hydrogenated vegetable oils also for diesel. And these are the new the feedstocks, the biofuel stocks that helps to reduce the CO2 emissions. But then European Parliament said, look, we have to pay attention not to be in competition with the area food. And so European Parliament limited at 7% the use of first generation of biocomponents, and then introduced the concept of advanced biofuels that cannot be in competition with the area food. Now, with the first draft of RED III that we have looked at, we see that the quantity of biocomponents should be increased and arriving at till 16% for the biofuels. This means that there is a huge effort that we have to do in order to create more biocomponents and in order to create fuels with low carbon footprint for diesel and for gasoline. And so for these reasons, we looked at this new concept of biorefinery. And so biorefineries played and are playing an important role today, but in the future we imagine the biorefinery with the future with a different feedstock, with feedstocks based on municipal solid waste and non-recyclable plastics. But why we are looking at feedstocks as such kind of feedstocks? Because waste, it is something that contains a lot of carbon. If you look at these slides, there are two important messages that I would like to deliver to the audience. One is that today we are the total waste, municipal waste produced in the world are in the range of 2 billion tons per year. And these 2 billions are expected more or less to double in the next 30 years. The second message that I would like to deliver to the audience is that in these municipal waste and in these non-recyclable plastics, there is still a lot of carbon, there is still a lot of hydrogen. So our idea is to take advantage of this hydrogen and this carbon and to create to reformulate new hydrocarbons. Now, in which way we can imagine this, let me say, new concept of a biorefinery. This new biorefinery can be organized in 3 blocks. In the first blocks, we have in our scheme a waste partial oxidation, where we create, and so no longer incineration, no longer a total full oxidation, but just a partial oxidation to create a syngas. Once a syngas has been generated, syngas will be purified. So there is a second block for purification, and then when we have the syngas purified, we can apply the existing technology to produce hydrogen, methanol, etc. But how our system works? It is in this slide. I would like to summarize how the system can work. First of all, our feedstock, it is not all the municipal solid waste, but our target is to have first of all, you have to recycle, to recover everything in accordance to the best procedures. To the best procedures. But once we look as a feedstock at the bottom of our pyramids, it is something that today is sent to the incineration. And instead of sending to incineration, we send this to our reactor. In this reactor, working around 1,000, 1,200 degrees C in the top, what is carbon and hydrogen is converted into syngas. So it is a mixture of carbon monoxide and hydrogen. In the bottom there is the part of the waste which is not contains carbon and hydrogen, is removed in the liquid phase around 1,080 degrees C, and then in touch with water we create a sort of inerts, a sort of vitrified products that can be used for the cement factories or also for ceramic industries. Now, it is also important to look at in this slide, you can see the waste composition on the left. It is where we base this material balance, and it is a very, very important data because looking with this feedstock, we can see that more than 95% of the product can be recovered. And so it is a lot. And the gas generated is washed with first with water, then with chlorhydric acid, and then there is a neutralization tower. And the bottom that we generate, so it is the part which contains inorganic components, it is more or less 16% of the waste. So our technology looks like a sort of full conversion, a waste full conversion technology. The only product that we have to deliver for as a waste that we generate, there are the concentrated sludge that we remove from the neutralization tower. It is in the range of 4%. This means that 96% of the feedstock is converted completely. Now, once the syngas is generated, of course, with this gas, the main products that we are looking at are methanol. And with methanol we can produce FAME, we can produce for diesel, MTB, but methanol, it is also very, very important as for the bunker oil, because methanol can replace the bunker oil. We can also generate directly hydrogen, and for, let me say, for the fuel cells, but also hydrogen that can replace also the shipping industry, part of the fuels in the shipping industry, and also green ammonia. But with the syngas, we can generate also ethanol, and ethanol can be used directly in direct blending for the gas. Or we can generate also methane. Now, okay, in this slide, without going into details, but I would like to leave the participants of this symposium, I will leave this material balance where I base this business case in terms of waste to methanol and hydrogen. And in our case, with the total material balance, you can see that with more or less 200,000 tons per year of waste, we can produce 90,000 tons of methanol per year and more or less 2,000 normal cubic meter per hour of hydrogen. So we imagine these schemes that are that allows the production of methanol and hydrogen. And in this way, with how the demand of hydrogen is increasing, we can increase hydrogen production and reducing the methanol. And the capex that we imagine for this unit, it is 220 million euro with such a capacity. Look, of course, at inside battery limits. And the IRR of projects like this are in the range of 13%. So double-digit internal rate of return, it is a significant figure when you talk about green economy. Then in this slide is also very, very important because the products that we are mentioned are the product that can generate important environmental benefit. Now it is, of course, we have to reduce the CO2 footprint. We would like to still produce products for our cars, for internal combustion engines, but of course with much less CO2 footprint. And in our case, the product that we generate, we can save more than 80% of the CO2. How we calculate this saving of 80%? Doing a precise LCA. And we compare the CO2 generated, let me say, in case of methanol, with the conventional process and with the process that we produce. So we look at the CO2 generated inside in our unit, and we deduct the CO2 generated from an incinerator, because if the waste became a feedstock for our units, this means that we don't have to use this waste in the incinerators, and conventional incinerators produce more or less 1.2 tons of CO2 per tons of waste, beyond all the NOx, beyond the particulates and other few pollutants. Now, but in this part of the symposiums, we are looking at refineries. In the introduction, it's been said that the refineries can be, during the CO2, this CO2 reduction roadmap, refineries can play an important role, can play part of the solutions. And so such kind of units can be located can be hosted in the refineries. Why? Because refineries is still a brownfield available. Because in the refinery we have existing facilities that can be easily integrated with our process. In the refineries, let me tell everybody that in the past, in any organization, I was twice a refinery manager. I know very well that in the refinery there is a huge knowledge available. And this huge knowledge available is something that is very, very important to operate such kind of units that can that are more or less like a conventional units that are present in the refineries or in petrochemical complex. And then oil companies are also the off-taker of the products, because if we produce ethanol, we produce hydrogen, if we produce methanol, they oil companies needs to produce biocomponents, advanced biocomponents, and so can be the off-taker. And then such kind of units in the refineries can give a contribution for the CO2 footprint reduction. Now, let me say now few words about the value of the products that we are going to generate, because such kind of units are significant, are important from a CapEx point of view. But what will be the price, let me say, of methanol? If we are going to produce methanol, what will be the pricing? First of all, let me say that in accordance to RED II, but also in accordance to the draft of the RED III, this kind of methanol is considered recycled carbon fuels. And part of these recycled carbon fuels that we generated is considered advanced biofuels. Why advanced? Because part of the carbon which is contained in the waste is from biogenic derivation. But look at the price. How we assess the price of this methanol? Because look, for the conventional price of the methanol now, the current price is more or less 400 euro per ton. And so we assume we start from the price of FAME. FAME is the value of the FAME is around 900 euro per ton, with 38 megajoule per kilogram. Our methanol has 20 megajoule per kilogram. So it is very easy to find the value. We divided 20 by 38 and we multiply by 900. And so we correlate the price of methanol with the price with FAME. If we would like to imagine the price of ethanol, for the price of ethanol it is more or less the same, making use of the price of ethanol in the market, which is 1,500 and 1,600 euro per ton. Go ahead. Okay, now in order to do this, we have, and to generate our concept, we have agreement in place with GFAE for the gasification section, where there are many gasifiers in operation, and they have been operating for more than 20 years. We have agreements in place with JM for methanol and hydrogen production, and we have an agreement in place with Lanzatech for ethanol. Now, let me, time is completing, I should be in time, but let me go to my conclusion. To summarize the concept of the conclusion, the technology that we generate as NextChem is a robust and commercially proven technology. Why it is commercially proven? Because it's a combination of, as I mentioned at the beginning, of 3 different blocks, and every block is that is part of this unit is absolutely is operating for a long time. Then it is this process represents in any case a viable economical project, and then waste is a valuable source of carbon that can be used. We call waste a sort of oil of third millennium. So it is a pity to treat the waste and to incinerate the waste to produce power. With the waste, we would like to create, with the circular economy approach, we would like to create new products. So a waste with this concept becomes once again a raw material. Thank you everybody for your attention. It's been a pleasure to me to stay with you, and I'm available to answer any question from the audience.
Thank you very much, Giacomo. Very interesting presentation, and I have to say we're going to look very differently at waste today, starting to see here some strong value in that. So thank you. A question first to open this You've mentioned this slide with the 2 billion tons of waste per year available currently globally, moving to almost 4. I'm interested to see a bit more what this means for Europe, because you have in your slide, I remember I saw it, Europe and Central Asia, which is difficult, of course, to isolate what is a European share. And in there, how do you think that the waste policy in Europe could influence a significant reduction of that waste and more or less limit the potential of your project, or not?
Okay, thank you for this for your question. First of all, let me say that if you look at the world, the advanced world, let me say, in the quantity of waste that normally is recovered is more or less 50%. The other 50% is sent part to incinerators to destroy, and then when you go to incinerator to destroy, but you produce also a tar as a bottom product that has to be disposed. And then there is a part, 20%, 15, 20% that is sent for landfilling. And now European Union states that starting from 2035, the maximum quantity of waste that can be allocated for disposal is at maximum 10%. This means that there is a lot of waste that can be treated with our schemes, and these schemes can, in the future, if we have to go in the decarbonized world, we can replace in the future the incineration, because if you incinerate this waste, you generate CO2, you generate NOx, you generate particulates, and at the same time, you generate a lot of CO2, 1.2 tons of CO2 per tons of waste. In our case, we limit a lot the generation of CO2, and we also maximize the use of electricity, of power in our process, in order that once the power will be green, of course, we will have achieved a much reduction in CO2 emissions. So in compliance with the directive, European directive.
Thank you. You mentioned in your business case for the methanol to hydrogen project an investment. You mentioned the capacity of production of methanol. Is this already a large production site, or is there big room for scaling up?
Let me say the order of magnitude of this project that I mentioned, 200,000 tons of waste, is considered medium size. We have in Italy, we have 2 other important projects in the south of Italy in 2 existing refineries. One is for 400,000 tons of waste, and the other one is for 600,000 tons. So it is 200 is considered, let me say, a medium size with 3 line in parallel in order to guarantee the maximum reliability of this process.
Thank you very much, Giacomo. We'll stop it here and we'll come back to you in our panel in about 23 minutes. I'll now hand over to Tijs Lammens. You are with me. Good morning, Tijs. So Tijs is process engineer at BTG Bioliquids and works on the development of application for fast pyrolysis bio-oil with a primary focus on advanced biofuels. Tijs has almost 15 years of experience in the area of bio-based chemicals and biofuels, PhD from Wageningen University, and subsequently worked at Shell as a biofuel researcher. You are now since 2018 in your current role with BTG, and you're going to tell us more about the projects that BTG is building and developing throughout Europe.
Yes, thank you very much for this kind introduction, and good morning to everybody. In my presentation, indeed, I want to talk about the use of fast pyrolysis bio-oil as a sustainable feedstock for the refining industry. And with that, give some examples of the projects that we are currently executing. Just trying to move to the next slide. It doesn't seem to be working. Sorry for that. There we go. So I split my presentation in two parts. First, I want to talk about our technology and our company, fast pyrolysis technology. And then the second part on the refinery processing of fast pyrolysis bio-oil. So again, next slide, please. So as a, sorry, there we go, back. Okay, there we go. So as a company introduction about BTG Bioliquids, we are a technology provider, so we supply fast pyrolysis technology, and we consider ourselves product leader of fast pyrolysis technology for biomass because we supply 3 commercial plants with our technology. Important to mention that fast pyrolysis bio-oil can be distinguished from vegetable oils, for example, because it is made from biomass residues, so it is considered an advanced biofuel. A short summary of our company history. In 1987, BTG Biomass Technology Group was spin off from the university to further develop this fast pyrolysis technology. And then about 20 years later, BTG Bioliquids, the company I work for, was founded in order to commercialize this technology. This resulted in 2015 in the first operational commercial pyrolysis plant in Pyro in the Netherlands. A year later, we signed a cooperation agreement with Technip FMC. I'll say a bit more about that later. And also we started a web shop to supply research and development quantities of the oil from Empiro to institutions that want to develop applications with it. And then recently, last winter, we started up in Finland, the Greenfield Nordic pyrolysis plant. And just a couple of weeks ago, we started up the latest project, the PyroCell plant in Sweden. So about the technology, fast pyrolysis is the thermochemical decomposition of biomass through rapid heating in the absence of oxygen. I'll say a bit more about it in the next process scheme. Important to mention is that you can use different types of lignocellulosic biomass as a feedstock, and it's all converted into one homogeneous energy carrier we call fast pyrolysis bio-oil. Byproducts of the process are heat and potentially also power. Here you see a scheme of the process as it is implemented in Empiro. On the left side, you see the biomass silo. The biomass goes into a dryer and then it goes up into the main unit from where the biomass is fed into a reactor. In the reactor, the biomass is mixed with hot sand to transfer the heat very quickly. All the biomass is then cracked into vapors, and then which are removed from the solids and the sand in a separator. The vapors then go through 2 cyclones into a condenser where the actual bio-oil is formed, and that goes to a storage tank, while the char that is produced with the pyrolysis process goes together with the sand and is together with air goes up into a combustor. In the combustor, the char is combusted, and that creates the heat to keep the process running and to further crack the biomass again. So it's a self-sufficient process. All the heat that we use is produced by the process itself, including the heat that is needed to dry the biomass beforehand. And then also there can be an excess of heat which can be exported to external clients and even turned into power if you want to supply the power for the plant. Overall mass and energy balance for these plants is 5 dry tons per hour of biomass comes in. 65% of that is turned into bio-oil, and around 30 to 35% is produced as steam. Then about the technology deployment, I already mentioned the 3 commercial projects. Here you see pictures of them. The first one in the Netherlands, in Pyro, it was already started up in 2015. And in 2019, we sold this pyrolysis plant to Twence because, we are a technology provider, not a pyrolysis oil producer. So for us, it's important to build the plants and supply the technology, but we do not want to operate them ourselves. And then recently, as I mentioned before, in Finland and in Sweden, projects were started up. I want to say a few words more about the PyroCell project in Sweden, because I believe it's quite relevant also for this symposium. PyroCell is a joint venture of Cetra and Preem, Cetra being a wood processing company in Sweden and Preem the Swedish oil refiner. It produces pyrolysis oil from sawdust. The plant started up this month in September of this year. It was delivered turnkey EPC by Technip Energies. So we have a collaboration agreement with Technip that they supply the pyrolysis plants using our proprietary technology. The plant produces about 24,000 tons per year of pyrolysis oil, and it provides a greenhouse gas reduction of between 80 and 90%. And then the Preem refinery in Lysekil will co-process the pyrolysis oil to produce advanced biofuels. Of course, this is in compliance with, for example, the EU Renewable Energy Directive, Annex 9. And then one last thing I want to highlight is that on the picture that you see on the right side, the modules were delivered. So we built the plants in the form of modules that are bolted together on site and then started up. So in a few months, actually, there's only a few months between the delivery of the plant and on site and the start. So that goes fairly quickly. Then about the application I want to talk about today, which is the refinery processing of pyrolysis oil to produce advanced biofuels. Let me start with the pyrolysis oil supply chain, because I think in that sense our thinking may differ from others, so I think that's important to highlight. We believe in the local processing of biomass residues, because the scales of the refining industry and biomass industries are quite different, and that was already mentioned as well. We built the size of our pyrolysis process to match the biomass industry rather than to match the refinery industry, and that has the advantage that you can locally process the biomass residues, so you don't have to transport them all over the place. You can return the minerals to the soil, and then you only transport the bio-oil once it's produced. So it's a liquid, which is about 10 times denser than the solid biomass. So it gives you quite some benefits for the logistics and the transportation. Then centrally, you can further process or co-process the bio-oil, making use of existing refining infrastructure. If you then talk about volumes, what you see on the picture is a sort of an average European fluid catalytic cracker. If you want to co-process 5% of bio-oil, you need 6 pyrolysis plants of the size that I mentioned for 50,000 barrel per day FCC unit, 5% co-processing, and that would give you about 2% of advanced biofuels in your product. So that's the kind of scales we are talking about. Then about the properties of fast pyrolysis bio-oil, I summarized them here. I don't want to go into all the details, but I want to show this picture first of all because, bio-oil, it looks like an oil. It's a dark viscous liquid, but actually when you look at the properties, it's fairly different. Half of it in terms of weight is oxygen atoms that are present in various configurations. Half of that again is water. So around 25% of the bio-oil is water. You can remove part of it if you want, but not all of it, because then your oil will become solid. So it is an emulsion of lignin fragments in sugar, as we call it, chemically speaking. It's not your typical refinery feedstock, and that is important to realize before you start co-processing this material. There are various routes in which you can process bio-oil into transportation fuels. What you see in this slide on the top is a very simplified value chain from crude oil to transport fuels through an oil refinery. And then at the bottom, you can see the conversion of biomass residues into fast pyrolysis bio-oil. which is the green lines, which can then be fed into an oil refinery, or they can first be further upgraded by hydrotreating to turn into either a stabilized pyrolysis oil, or it can be completely deoxygenated into a product that we call mixed transportation fuel. I will say a few words about it in the rest of the presentation. So bear with me on all the shortages, the SPO, MTF, etc. But important is that the fast pyrolysis bio-oil route is the main part I want to talk about, because co-processing, it uses existing infrastructure. It's very low in capex compared to other solutions to produce biofuels. It can give you a short time to market. Essentially, it's already commercial, and with that, it can lead to fast greenhouse gas emission reductions. The gateway for fast pyrolysis bio-oil is the fluid catalytic cracker, because I already showed the properties, and FCC can deal with this amount of water and oxygenates that are present in the unit, and also with the coking tendency of bio-oil. Of course, there are a couple of challenges when you use an FCC to co-process fast pyrolysis oil. There are many different outlets for the products. That means also that the biocarbon ends up in many different products, and then it is a challenge to track the green content. Here you see a scheme of how it works, a very simplified FCC scheme. You see the black arrow at the middle. I'm not sure if you can see my pointer, but you see here the VDO going at the bottom of the riser. There's a green addition, a separate feed line for pyrolysis oil. It needs to be separately injected because you need to keep it relatively cool, below around 60 degrees, before you inject it to avoid coking. But then once it entered your unit, the biomolecules will be cracked immediately with a regular feed. So the acidity will disappear. Also, the coking tendency will be much less. And well, as I mentioned, it's cracked together with the rest of the regular feed into all different products that you normally produce from your FCC, such as gasoline, LCO, etc. Commercial operability of this process has been proven in refinery trials of several days, up to 5% bio-oil. And also at pilot scale, it has been shown that you can even go up to about 10% bio-oil co-processing. Then the yields. If you co-process about 5% bio-oil, it has very little impact on the overall FCC product yields, which is what you expect, of course, if you only co-process 5%. You can see some general trends. Relatively, the gasoline yield increased. The LPG yield stays around about the same, and some of the other yields decreased slightly. This is based on literature data that were published by Petrobras. Of course, it differs from one unit to another what happens exactly to the yields. But in general, what we see is that gasoline yields relatively increase if you co-process bio-oil. And that's also what's depicted here in the graph. You see a relatively high yield of gasoline from pyrolysis oil co-processing. So these are sort of the observed yields from the bio fraction that have been calculated. So you see a relatively high amount of gasoline, some LPG and LCO, and of course CO, CO2 and water. So all the oxygenates that are present, they are turned into carbon monoxide, dioxide, and into water. Then there are some other refinery pathways that you can apply for processing fast pyrolysis bio-oil into advanced biofuels. One of them is hydrotreating, so you can do it standalone. Important when you hydrotreat pyrolysis oil is that you first do a stabilization. I already mentioned there's a significant coking tendency of bio-oil, so if you put it into a regular refinery hydrotreater with a fixed bed, you will probably coke that, and it will, you get high pressure increase relatively quickly. So there's a mild process that you need to do to turn the sugars into alcohols, essentially. and to remove the coking tendency of the bio-oil. That's what we call the stabilization step, and that results in a stabilized pyrolysis oil. The stabilized pyrolysis oil can then be further hydrotreated in regular processes like a nickel or cobalt molybdenum-based hydrotreatment step. And then you finally produce completely miscible deoxygenated biofuels. Sister company of us, BTG Next, develops a demo plant for this process in order to produce marine biofuel of about 1,000 tons per year, which should be ready by 2023. And that should prove this process. Then if you have produced a stabilized fast pyrolysis oil, so the SPO, you can also use that to co-process it. So you don't need to necessarily use a hydrotreater, but you can again enter it into an FCC unit. The big advantage here is if you first stabilize the pyrolysis oil, is that you can co-process higher volumes, up to 10 or higher than 10 weight % of the crude pyrolysis oil, and it also provides a higher biocarbon yield. So for the longer term, that's a nice step-up way of increasing the amount of bio-oil that you co-process in your unit. The next way is gasification. There already has been some presentations on gasification in this session. What you can also do is gasify the pyrolysis oil. This has a couple of advantages compared to gasifying solid biomass directly. Most notably, of course, the logistics is much easier, but also the bio-oil contains a lot less minerals, for example, than the biomass itself. So in terms of the purification process of your gasification, there are also significant benefits. And then from gasification, you can make all sorts of products that have been mentioned already as well: DME, methanol, Fischer-Tropsch fuels, hydrogen, etc. This has been shown already that you can gasify pyrolysis oil in 2002 by Shell and also in 2012 in a black liquor gasifier of ETC. And then last but not least, hydrocracking. If you want to use a regular fixed bed hydrocracker to co-process or process bio-oil or fast pyrolysis bio-oil, you first need to upgrade it, at least to stabilized pyrolysis oil. But the Ries Institute in Sweden recently also showed that in a slurry hydrocracker pilot plant that they could process 20% of pyrolysis oil without operational problems. And that resulted into a significant amount of biofuels. So that's what I wanted to say about fast pyrolysis bio-oil. It has reached the commercial maturity from a production perspective. There are currently 3 operational commercial production plants of fast pyrolysis bio-oil. If you want to use it to produce advanced biofuels, it has a high potential compared to other routes. It's low in capex. It's a very short time to market. And you can, with that, achieve fast greenhouse gas emission reductions as a refinery. Feasibility of pyrolysis oil co-processing in FCC is proven up to 5 weight %. There have been commercial scale trials, several around the world. So it's been shown that it works. It's been shown that you typically have a favorable gasoline yield, but of course the exact yields depend on your unit, on the type of feedstock that you use, on the exact process conditions, etc. And then there are also other refinery pathways for fast pyrolysis bio-oil besides the FCC, which are at various stages of maturity. So there's hydrotreating, hydrocracking, and of course also gasification is a very good option. That's it for my presentation. Thank you very much for listening to me, and thanks very much for the organizers to give me the opportunity to present our projects and the applications for fast pyrolysis bio-oil for the refining industry. Thank you.
Thank you very much, Tijs. We're a little bit short in time, and I will have to move quickly to the panel. Nevertheless, I have 2 very small, quick questions I would like to ask to you. Firstly, is it possible to have a 100% drop in fuel of fast pyrolysis bio-oil?
Oh, yes. All the routes that I presented here result finally in a complete drop-in. So the bio-oil itself is not a drop-in, but there are various ways in which you can process it to turn it into a drop-in fuel. Yes.
Okay, thank you. I have also some questions from the audience. I have one that asks, what is the impact of the feedstock source and quality on yields?
There is an impact. So there is an impact on the pyrolysis process if you have a relatively high amount of ash in your biomass. So, for example, if you use agricultural biomass, sunflower husks, straw, those kind of products, there's relatively a lot of ash that increases the cracking tendency of the pyrolysis process. It catalyzes these kind of cracking reactions. So that means that you get relatively a bit more steam production and a bit less oil production. So you see the bio-oil yield decreasing from 65 to around 60% or so, and you see the steam production increase a little bit. So it shifts the yield a bit.
Thank you.